I'm going to talk to you a bit about my favorite element of all the possibilities from the periodic table. My personal favorite is actually the element next door to carbon, and that's boron, this little beauty. So you can see the two important numbers associated with boron. You've got the number 5 here, which is, of course, its atomic number. It's how many protons an atom of boron has. That's why it's the 5th element. And but the second number here is the total number of the total mass, the atomic mass of the average boron atom. And it's not a whole number, it's 10.8, which is interesting. That means it's got a number of, well, 2 isotopes. So most of boron is found with 5 protons and then 6 neutrons, which would bring up to boron 11. But 20% of the time, 20%, which is a large fraction for a light element, it has a second isotope, boron 10. And that's a very important isotope, which has all sorts of other applications, which I'm going to come to shortly. But boron is a really unique element in the sense that it's not made in the usual way. And when I say made, elements, the lighter elements in particular, certainly all the way up to iron, are made through nuclear synthesis in stars. So in the cores of stars where we get nuclear fusion, where lighter elements are compressed and they overcome the repulsive forces to squash together and to form new, gradually heavier and heavier elements, all this occurs in the stars. And but in the case of boron, there's no mathematical way to get to the 5th element. You can't add up gradually the heliums with more hydrogens with more heliums to eventually get to boron. So it's really a puzzle that it exists at all. And it exists, in fact, in a similar way to how uranium exists. It requires a supernova. It requires the star to explode to really generate enough energy to fragment a lot of the heavier atoms and recombine these elements into other forms. And from these huge events, you can get boron. And eventually some of that will be in the nebulous, which forms planets like our own. And thanks to that, we have boron as well on this planet. And we find boron on this planet as we find most elements, as an oxide. Here's a sample of boron oxide. Like most things, it's a white powder. But boron oxide has quite an interesting history in terms of what people have done with it over the ages. So these salts of boron oxide that we find, they were called borax. And their first uses were found by the ancient Egyptians. And the ancient Egyptians found mines of borax in what is today's Turkey. It was then part of the Hittite Empire. And they discovered that these borax salts were very good at desiccating, at extracting, removing water from things. And it became very useful to the ancient Egyptians for the mummification of bodies, in particular pharaohs, of course. And so it became a very expensive and important material for this ideal way of desiccating the body quickly, removing the water to ensure a perfect mummification process. Later on, ancient Romans, they discovered when they were making glass, that's because, of course, glass like this is mainly silicate, so it's mainly silicon oxide, sand. But they found that, well, if you add a little bit of borax, a little bit of boron, then the actual properties of the glass somewhat change in that it becomes far less fragile. And in particular, it can cope with huge temperature shocks. So I've just poured here the coldest substance that we have readily available for us, and that's liquid nitrogen. So that's minus 196 degrees. And that thermal shock, though, is not enough to make this glass crack. And that's because of the boron that's in this silicon oxide, which is implanted there. If you add a bit of borax salts into the glass mixture when you're heating it up, and that gives this wonderful property. And indeed, to today, the use of borax salts into various ceramics is a very important and part of how it's marketed and how it's sold into the current days, markets, and how boron figures in our industries. But what I want to concentrate on today is something that happened in 1912. You see, 1912 is a year that, if you've seen the film Titanic, where the great ship Titanic sank. And on that same year, well, there was a person who did a remarkable bit of chemistry. He managed to replace the oxygen in these borax salts with hydrogen and form, thus, the first boron hydrides or boranes. And in fact, my first question to you today is, which chemist synthesized the first boranes in 1912? Anyway, the chemists who did manage to do this, he discovered really a new boom in inorganic chemistry. This is the gentleman here, Alfred Stock, a genius. He also did some amazing. His supervisor, PhD supervisor, was Emil Fischer. He did some amazing work in organic chemistry. He also announced to the world that it's a shame that our planet has this remarkable process of photosynthesis, which is unique to carbon, which turns the oxide of carbon, carbon dioxide, into a hydride of carbon, and hydrocarbons, which of course are the be-all and end-all of organic synthesis of our beginnings and life and color and everything on this planet. And he was keen to set his PhD students, the best of which was Alfred Stock, to look into these other elements. Are there other elements that can form a series of hydride compounds? And Alfred Stock came up with the hydrides of boron, the boranes. Now, you've seen in the previous talk some of the structures that carbon makes. They tend to be these flat, ring-like or chain-like structures. Well, Alfred Stock realized and found out that boron, with its hydrides, form these amazing three-dimensional, very beautiful, what are called polyhedral structures. Here's a 12-vertex icosahedron. And so these boranes suddenly began to increase in their number, more and more synthesized, and they realized that boron, after carbon, is the element which has the greatest potential to form hydrides. I want to talk about and show you what some of these hydrides can do. Okay, so here I've got, what I'm going to do is going to put this little dish in front of me here. I've got a small amount of boron hydrides here dissolved in a solvent, and I'm going to pour it out here onto my plate carefully, because in the same way as hydrocarbons are very useful to us as fuels, well, it didn't take long before the boron hydride chemists discovered that boron hydrides also oxidize in air. But when they do so, and I hope you can see that nicely, it gives a wonderful big difference to if I burn carbonaceous materials in oxygen, we get this orange flame. Whereas here, if I take the boron hydrides, they give a wonderful green flame. Now look at that. And often actually during some of the major projects which were developing boron hydride chemistry, they called those projects the Green Dragon. Now, it didn't take long before they recognized they could calculate how much energy is being given off via this oxidative process with boron hydrides compared to carbon hydrides, which were the fuels of the day. And they realized that, and they calculated, and they also measured that this oxidation process of the boron hydrides is giving off much more energy per unit volume than if I use hydrocarbons. Well, that led to a big boom. What happened next? Because you see, now we're talking about the 1930s, 1940s, 1950s, and it was all about, let me get this the right way around, it was all about trying to find rocket fuels. So here in the Czech Republic, in Rzesz, where I have my labs, there are some top secret research works looking into the boron hydrides as a potential new rocket fuel. Now, I'm going to show you how we can go from an oxidation process, an easy one, such as we've just seen here with the burning of boron hydrides, and ramp it up to actually get a rocket propulsion. It's not actually that difficult and something you can do in your schools or even at home if you're very courageous. And indeed, you don't need a lab like mine to be able to make the boron hydrides. Borax, the salts of boron oxide, can be found in many different products that we find at home. They're often in washing powders, for example. And if you dissolve borax, salts of boron oxide, in alcohols, you can form these boron esters, which have a similar effect. If dissolved then and burnt in alcohol, you'll also get that nice green flame. Now, in any oxidation process, especially with the boron hydrides, which are releasing its energy, which are in these bonds, so you've got your boron hydride molecules, which have these wonderful polyhedra. All the energy is trapped inside these bonds. And when you get oxygen coming through, you begin the burning process, you're forming new molecules of boric acid, boron oxide, and water. And that reaction is very quick, very fast. All the old bonds are breaking and new bonds are being formed. And that's releasing the energy difference between the older bonds and the new bonds as the energy is being released. And if that reaction happens quickly, then we get a big expansion of gases which are being produced. And that expansion of gases can act as a reactoring force and a propulsion force for a rocket. So all we need to do really to make a rocket and make some rocket fuel is to have the right chemistry, as we have here, and then you just need to force those new molecules of gas that have been formed to go through a small area and therefore create a propulsion force. So this is essentially all you need to make as a rocket. You just need a bottle with a cap. Now the cap, I've just put a hole in the middle there. Can you see the hole there? You can see the hole there. Right there in the middle. Well, that hole is what I'm using to really confine the space, to force these molecules that have been formed inside our rocket to come through, to really push through this confined area to come through. So that's how I can get the propulsion force. Then, so inside my rocket, all I do is I put a bit of fuel. I don't need much at all. I'm going to shake it a bit. I'm going to use my hand just to warm this boran alcohol mixture up, just to get the transition to vapors, so it's mixing with the air a bit better. On the top here, I've just sellotaped a simple straw, because I'm going to use that to guide the way my rocket's going to fly. And I've got along here a simple piece of string. Push it through like that. Okay, now I just need to empty my bottle of the remaining fuel carefully onto the floor. I'm going to go back over here. Okay, it's all tight and ready. Now, hopefully you can still see this. I'm going to take my fuel over here. I'm going to take my lighter. Are you ready? Can you see it all? Ready? Countdown. 3, 2, 1. So that's it. We got the propulsion that we needed. That rocket really did fly. I only needed a very small amount of my fuel, the boran fuel. And I want to explain, though, how eventually the boranes didn't become the rocket fuel of choice. And that's for the following reason. When I burn hydrocarbons in oxygen, I form carbon dioxide and water, both of which are gases that can leave the engine of the rocket without any sort of deposition of anything. Whereas when I'm burning boron hydrides, I'm forming water, but I'm also forming something else. I want to show you it here. Here, can you see it on the camera? See that white? That's boron oxide. So the oxide of boron Whereas the oxide of carbon, carbon dioxide, is just a gas that would leave the engine of the rocket. Well, when we use boron fuels, the problem is you get accumulation of boron oxide, and it's a white powder. And that white powder will eventually stop the rocket from working. So you get a lot of initial energy and a lot of initial acceleration, which is superior to normal rocket fuel. However, the accumulation of this white powder destroys the actual trajectory eventually. Nevertheless, I think even Elon Musk's SpaceX thingy rockets, they do use a little bit of boranes at the beginning to get the initial thrust. But to finish with, I want to show you, of course, today's rocket fuel that's used. And today's rocket fuel is today's rocket fuel is none other than, almost broke the dishes there. There's another end, what I've got over here. Here we go. This is today's rocket fuel. It's, of course, hydrogen gas. And hydrogen gas gives a wonderful oxidative reaction, which you're going to know, and you'll probably be familiar with. Let me just position this balloon in the right place. Let's get it onto the floor. Here we go. Now, this, don't try at home, kids. What I'm going to do here is I'm going to just show you the real rocket fuel of today. It is, of course, oxidizing hydrogen to give water and a lot of energy. 3, 2, 1.